with me. Right, so I'll talk about this other model in which we can try to do estimation. And the algorithmic technique here that I'll introduce will be approximate message passing. And okay, I'm not going to say too much about how this generalizes to other model, but it does. AMP has tremendous power, and you'll see that in 2 talks. We'll see that from Shubha talk, perhaps tomorrow, is that correct? And from Pragyasur's talk this afternoon. So the basic vector that we're trying to estimate is x0. I'm going to call that the signal. So now it's n-dimensional. And let's just suppose that the coordinates are drawn IID from some prior unit variance. Okay. Now I observed the following observations, or following random variables. 0i x0j plus wij. Here I is smaller than j, between 1 and n. And wij is Gaussian. So I just showed you, so this is a matrix, of course, right? It's symmetric, and I only define these values, but these values can be defined by symmetry. I don't care about what happens on the diagonal. That's why I considered I strictly smaller than j. You can put whatever you want on the diagonal, it doesn't matter. Right, so this is a matrix model. And okay, suppose we want to estimate x0. So what is one estimator that you could use? Very simple estimator. Once you estimate x0, you have a matrix. Matrix looks like this. Rank 1 plus Gaussian matrix. Right, so we have a rank 1 perturbation that will push the eigenvalues, presumably, to push the eigenvalues somewhere, push them up. So one thing you can try to do is compute the first eigenvector and see whether it aligns with x0 or not, right? So eigenvector, first eigenvector. First eigenvalue eigenvector. Now, this is a random matrix theory problem. It's not a very hard one. And then you can analyze exactly the performance of the performance of this estimator. How much does it align with x0? So it turns out, since I chose my prior to be mean 0 and variance 1, specifically the variance 1, the phase transition happens at lambda equals 1. So if lambda is greater than 1, then lambda max of this matrix will be strictly larger than 2. It'll be lambda plus 1 over lambda. Strictly larger than 2. And 2 is the relevant quantity because the spectral norm of this matrix is 2. It's a semicircle law, right? So the eigenvalues of this matrix look like this. Minus 2, 2. If you normalize by square root n. So as soon as lambda is larger than 1, you get an eigenvalue that pops out, right? So not only does the first eigenvalue pop out, but also when you look at the first eigenvector, call it v1, you look at how it aligns with x0, you divide by n, so this is the inner product, right? That will converge to a quantity that is well known, that is like this much. And this is strictly positive if lambda is greater than 1, right? You can see that. On the other hand, if lambda is smaller than 1, then the first eigenvalue will stick to the edge. Converge to 2. This is converge. And this quantity will converge to 0. So you're orthogonal. The first eigenvector is orthogonal to the signal. So you cannot do anything with that. Now, as we did with maximum likelihood for the previous problem, you can ask whether this is the best thing we can do or not. So this question has 2 aspects to it. Can you beat this threshold 1? Can you estimate below 1? So that's the first one. And the second question is that even if you're above 1, whatever lambda is, whenever you can estimate, can you get the best overlap, right? So this spectral estimator gives you this overlap. But can you do better? Is there another estimator, let's say, that works also only when lambda is larger than 1, that gives you a value that is larger than this? So there are 2 questions. You can try to answer them both. Okay. Now, let's try to apply what we've seen in a previous lecture. So we can write down what the posterior measure of the signal given y is. So if you write this down, we can do the Bayes rule, right? And that will be, let me just write, times exponential. Since this is also a Gaussian additive model, this is a signal plus noise. It's said that the signal has a more complicated prior structure, right? But that doesn't matter as far as the Bayes rule is concerned. So we get I smaller than j, lambda over squared n yij. It's basically the same expression. Right, d p0 to the power n of x. And the free energy and of lambda is 1 over n log z. Take expectation. Now you want to understand, as we did in the previous example, you want to understand whether this thing has a limit or not. No, it does. And this is a theorem. Let me write it. So this is called the Replica symmetric formula. It says that for all lambda positive, Fn of lambda will converge pointwise as n goes to infinity to a variational formula called Vrs of lambda. And this is more or less explicit. It's an optimization problem over 1 variable. It's a supremum over all q, which are positive. I have a function psi that I'm going to define. Lambda shows up there, minus q squared over 4. Right? So what is psi? Psi is the free energy of the additive Gaussian, univariate Gaussian additive model. So if I observe, as in the previous lecture, y that is given by this, so this is real, this in 1 dimension, then phi is the free energy of this model. R over 2x squared dp0 of x. So you can say perhaps one mystery here that you can ask is, why does the free energy of the 1-dimensional problem show up in this problem? And here we're looking at a problem that is presumably more complicated. It has interactions between the coordinates. So xi is, this is a rank 1 matrix, and the entries of that rank 1 matrix are dependent, obviously dependent on each other. They're xi, xj. But yet you still get something that is decoupled across coordinates, right? So we'll try to answer that, and I'll give you some heuristics about how to compute this, and I'll tell you something about the rigorous proof. So this theorem, okay, this has a long history. I don't know who to attribute this to. Let's say, Zakala, Stivolva for the non-rigorous. And then we have Kabashima, that was even earlier than that. Nishimori, even earlier. This is like the 80s or something. Rigorous proof is much later. So, okay, I can attribute it to Lollard and Yolan. This is maybe 2017. And Abbe, Deshpande, and Montanari. Let me write it here. And I am sure I forgot other people. Yeah, they proved it in various levels of generality. I think this paper gave the cleanest proof to my taste. And I'll show you, I'm not going to show you really the proofs. I'll show you some heuristics on, so the method, this talk is about the methods, and I'll show you some methods to guess this type of formulas. Okay, so this will be perhaps an occasion to introduce what is called the cavity method. I'm not going to spend too much time because this is a computational method and I don't want to spend 10 pages doing computations, so I'll just give you the main ideas. So we have a function that looks like this, and you want to compute the limit. So a priori, it seems like a very challenging thing to do. If you push the expectation inside, you're not going to get anything interesting. So the annealed free energy is not giving you the right answer. You cannot just push the expectation inside. So there is this Landmine analysis. So this is all about analysis, right? So this is, everybody knows this. If you have a sequence of real numbers such that this sequence converges, then the average converges to the same limit. Okay, obvious. And we can try to apply this to this problem. So this is your sequence. Okay, you don't know whether this converges. You would like to make sure that this converges, but you can write it as an average. So in particular, if you apply this, if you can show that fn plus 1, okay, divided by n. Let me do log of zn plus 1 expectation minus log of zn converges to some function phi, then fn of lambda will converge to that same phi, right? Because this is your an sequence. Now, if you take this and average, then this is the lemma, right? Okay, so why did I write it like this? Now, because of the logarithm, when you take the difference, you just get zn plus 1 over zn. And then so here you have a system of n plus 1 variables. Here you have a system of n variables. So you're just taking your system of n variables, you're adding one variable to it and see what happens, right? So this is where the name cavity comes from, or perhaps it's the reverse operation. You have your system, you take one element out instead of adding it, it's the same thing. And you create a cavity, right? And then you look what happens in that cavity. And anything that happens in that cavity will tell you what the limit is, right? As long as you can make everything works. So this is, okay, this is old, and people have realized this for a long time, since the 70s in physics, and statisticians also have their own version of this that is called the leave one out method. It turns out that it's the same thing. Perhaps Pragya is going to talk about the leave one out. Right. So if you want to do this computation, you're going to have to make some heuristic assumptions about what's going on, and we'll try to explain what that is, what those are. So let's try this. And I want to do this perhaps just graphically. I don't want to write too many expressions. So here in this model, every I talks to every other j, right? The matrix is dense. We had a matrix that was dense, right? So a graphical way to represent this is just the complete graph on n vertices. Now I add a new element to this graph, so I get a kn plus 1, right? And it's connected to every other guy here. So this is my vertex n plus 1. Now, if you try to isolate the behavior, isolate the effect of what this kn has on this new variable in the Hamiltonian, try to understand that will give you the answer. So if I write hn plus 1, so this is my Hamiltonian, hn is my Hamiltonian. So it's whatever appeared in the exponent here. So if I write hn plus 1, what is that? I have So I have to put an n+1 here, excuse me. I have to put an n+1 here. But let me just separate that, as I said. I'm going to separate the effect of kn over the new variables. So I have the first n variables that interact among themselves, and I don't care for now. n+1 xi squared xj squared, right? And now I have the effect of all of these lines here. So this thing accounts for kn, for whatever happens inside, right? Now I have the effects of these lines, and I can add them up. So I have I from 1 to n, lambda over n+1, I n+1, xi xn+1, xi squared, xn+1 squared, right? So let me call this new thing, let me call it little h. So x from 1 to n, I'm going to denote, okay, so let me change notation so that everything becomes a bit simpler. So this is x, xn+1, and x is the n-dimensional vector. Right. So this is a function of x and xn+1. And now I'm going to, again, change notation. Xn+1 will be epsilon. Okay, so the new variable that I'm adding is epsilon. So you can see that kn acts on epsilon in a linear fashion. So this is a sum over tens. You can do this, right? And same thing for this one. So it acts with a field that is random. So continue. Let me expand what y is. So y is whatever the expression is. Let me expand that. So I have lambda over n+1 y I n+1 xi epsilon plus lambda over n+1 x x0i xi epsilon 0i epsilon 0 epsilon minus this term. Epsilon squared. Okay. Good. So now if you draw, so what happens here? When you look at zn+1 over zn, this is the quantity that you really want to understand, right? Because that will give you that value.
Sorry, what's x value? X0?
X0, so let me write it again. So where should I write it? So y is yij is lambda over n 0i x0j. So I put 0 when I refer to the planted signal, right? And you have a y here, yij. And epsilon, of course, so this is in n dimensions, but if you do the n+1 dimensional thing, you have an n+1 here, right? And then x sub 0 n+1 is epsilon 0. So this is just an it's really just an expansion of this. Just expand this and you get that. It's really nothing happening, right? This is what you get. What is this? This is the integral of exponential hn+1. Hn+1 is that. So it's just hn. Okay, let me remove the +1 here, all right? Just for the sake of illustration. This is false, but let me just remove the +1. And let me remove the +1 in here as well, and here as well. Right? So that's h of x. So I have this and that. So I just split the prior, since it's IID, so this is an n-dimensional prior over x, and then the prior over epsilon, right? But then Zn is Zn. Yeah? Ignoring the n+1 in the denominator. Denominators, these n+1s. Right? They're going to have an effect. You cannot ignore them, actually. But if you write it like this, then you see what is this? It is a Gibbs average of this quantity. Right? So if you just split this integral, take this inside, right? And this is really just Gibbs average of this quantity, right? So this is what I mean by that picture that I drew. You have a system of n particles that interact between them using their own laws, right? They're drawn from the Gibbs measure on n particles. I mean, they're n particles. And then they act on the n+1th variable that I'm going to call epsilon here through this random field. Right? They act with an external field that is linear. So if you can understand the law of this external field, then you can perhaps get an expression for this. Right? So what does this field look like? And I wrote it here. I can separate this contribution from the rest of the contributions. So we're going to see why. If you have a question, please just stop me. So H epsilon, I'm going to write it as, let me ignore the n+1 again. Epsilon, I'm going to put this guy just close to it right here. Squared, and I'm going to isolate this term. Lambda over n, ignoring the n+1. I, 0I, epsilon 0 epsilon, right? Okay, let's stare at this for a little bit. This is a Gaussian. They're inside the exponential, right? This whole thing is a Gaussian process that is indexed by x0, by the x vector x. Now, if you look at this quantity, it's an average over this inner product. So it's an inner product between this vector and the signal, right? Signal vector. And this x is drawn from the Gibbs measure, right? So draw x from the Gibbs measure, right, with n particles, and look at the overlap divided by n between that draw and the x0, right? The planted signal. Okay, so if you expect there is concentration of measure, if you expect that this guy concentrates, I can just take this average and replace it by a single number. Okay, let's do that. So the main assumption. Called the replica symmetric hypothesis. I'm going to write it a bit more mathematically than what the physicists will write, but the hypothesis is there is a Q such that this thing concentrates around Q. Okay, so I just put the second moment there just because I like it. I like the second moment. Right? There exists a Q such that this is true. Now, if that's correct, then I can look at this expression and I can replace Q here. Right? Now let's look at this thing. So this is a Gaussian process, as I said. Let's write it as a Gaussian process. So this is.
So just to understand, this is a hypothesis because xi's are drawn from the posterior and you don't know whether that concentrates or not.
Correct. Correct. Exactly. So let me write this process. Let me just write here. This whole thing is z of dots, right? So it's a Gaussian process that is indexed by x and epsilon. It's centered. You take the expectation of this thing is 0. Okay, so this is a Gaussian process. But when you add this is a geometric thing, right? This is, you know, if I have a Gaussian random variable and I take the exponential of it, if you take the expectation, then you get whatever it is. So if you take sigma here, you get exponential sigma squared over 2. If you subtract the thing, then the expectation of this thing is 1. So this is an exponential martingale somehow, right? So this thing just normalizes this Gaussian process so that when you take the expectation of the exponential of this thing, it's still 1, right? So let me ignore this part. As long as you can understand the first term, then this thing will just normalize it. Now I said the expectation of this thing is 0. Now it is the covariance structure of that thing. Gaussians are only determined by means and covariances. The mean is 0, is the covariance. One, 2, 2. Right. What is that? So it's lambda over n, the sum 1 to n. Then you get xi1, xi2, epsilon 1, epsilon 2, right? Is that correct? I just took this thing and I multiply it by itself, but for a different test vector here, right? That's what the covariance is. So now you still get the same kind of expression that we got here, right? It's a Gaussian process whose covariance has this form, and you're asking whether now does this concentrate or not. And of course, it doesn't make sense if you ask that for an arbitrary x1 and x2, but the point is you're only looking at x1s and x2s that come from the Gibbs measure. If you draw x1 and x2 from the Gibbs measure, right? Now look at the covariance of this Gaussian process with those tests, those vectors as test vectors. Then this is the covariance, and if this thing concentrates, then I can replace this whole thing by a constant again. Right? But I claim that I already made that assumption. Right? So this is the same thing as this because of the Nishimori property. Right? X0 is the same thing as x1, x2. So I've already made that hypothesis. So I know that this thing concentrates. Right? So this whole thing is about lambda q, epsilon 1, epsilon 2. Right. Now, if you have a Gaussian process that is mean 0, and you know the covariance, you can just replace, the only thing that is interesting here is the law of that process. So I can just replace it by another Gaussian random variable that has the same mean, the same covariance. And there's a particularly simple one. This is just z times square root q. That's another Gaussian that has the same mean and it has the same covariance. Right? So if I replace z x epsilon by square root lambda times q, there's a lambda here, right? Times z and epsilon. Right. Now, if you want the expectation of the exponential of this thing to be 1, you're going to have to subtract lambda q over 2, epsilon squared. Right. So that's where this term is going to, replace this term by this term. Now, if you do this replacement, the q z times epsilon. If I do that replacement and I put everything here, that's still, so now I remove these brackets because I know that the things inside concentrate around those q's, and then I can just remove the brackets because there's nothing around them anymore. I get exponential, what? I said the first term will be replaced by this minus, of course, the right thing that concentrate that normalizes. Z epsilon minus lambda over 2, lambda q over 2 epsilon squared, dp0 of epsilon. Okay, now this term was replaced by lambda q epsilon 0 epsilon.
Are you assuming anything about Q?
There exists a Q that satisfies this. Q is deterministic.
Oh, it's deterministic.
Q is a deterministic constant, yes.
Yeah, how do you show? I was just curious. How do you show replica symmetric hypothesis? Do you differentiate that quantity with respect to lambda?
You have to work hard.
That's how you do it, like the strength of practical model. Differentiate with respect to temperature.
So what you can try to do, there are many ways of doing it. So you can do a recursive thing, like you're going to start peeling off one by one. There's another way to do it where you really just use the derivative of free energy, prove that the Hamiltonian concentrates. There's a lot of work. I'm not going to talk about how you prove this. So let me just continue this, and then perhaps I can come back to your question a bit later. So we see here, so what is this? This is really just if you put a log here and you put an expectation outside, that's really just the free energy of the one-dimensional model, correct? With a specific Q. So that's how you get the answer that I erased. But you see there was a lambda Q, so the replica formula was this. If lambda Q minus lambda Q squared over 4. I only showed you how to get this term. I did not show you how to get this term. But this term comes exactly from the contribution of replacing n by n+1. So when you do the real computation, when there is an n+1 here, that n+1 has a non-vanishing contribution that will get you exactly this q squared over 4. So I have notes on this, like it's maybe 2 pages of derivation. It's not really complicated. And yeah, I'll give it to the organizers if they want to share it. But this is really what the cavity method is about. You just put another variable and then see how the system acts on that variable. If you can understand that action, then you can write down formulas. So how do you prove this? This is the main thing. This is really how like the proof works. You really have to work hard. I don't want to get in there. This is the main crux of the proof.
Yeah. So you look at tensor models, the same thing.
Yeah, that's correct. Same hold. Same, exact same thing. Everything's
like
same.
Model, same free energy.
Yeah. Yes, yeah. So because the spike tensor is the same, you know, it's also a Gaussian additive model. It's just in a more complicated. Yeah. So as long as you're doing Bayesian inference, right? So this is a a statistical inference problem. They're all replica symmetric. Why they're all replica symmetric? Exactly because of the Nishimori property. So if it wasn't replica symmetric, I wouldn't know that these two things with the x0 and x1, x2 are the same. So I would have to have 2 parameters, right? Q and rho, whatever. So this thing will concentrate around Q. This thing will concentrate around rho. So I would have to prove both, concentrations. That doesn't hold always, as you very well know, right? At low temperature, right? Are there other questions about this? Perhaps this is like some impressionistic derivation of the cavity method. That's all I can talk about now. Okay, so it's already past half the time and I haven't talked about AMP. So let me talk about AMP. Let me just tell you another way of doing this. It's called the Guerre interpolation. This is really a workhorse in this field, interpolation. So you're going to interpolate between this model, this complicated model, and a more simple model. And what is the simple model? Is the model where everything is decoupled, as we've seen from here. From this derivation, it gives you a hint that there is a relationship between this matrix model and the decoupled model, where you have just IID observations. So that's what this does. I'm going to consider a system of two pieces of observations that are parametrized by T. This is the first one for t equals 1, then this is the original model. And I'm going to look at another piece of information, which is given by lambda q, which is the q is the same. It's a parameter of the problem, and I'll put a 1 minus t here. And now I'll just put an x. This is a vector plus z, and that's some other vector that is a Gaussian. So this is an additive Gaussian model where the coordinates are IID coordinates. Right, so observe these two. So at time equals 1, you get this. At times, yeah, correct. Time equals 0, this goes away, and you only get the decoupled version. Now this is another, so I give you these two observations, and I ask you to estimate x, and you can do the same thing. So you can write down the posterior measure, you can write down the free energy of this model. This is another statistical inference model, right? You can write down the free energy, and that will depend on t. Let me call it this. Now, if you take a derivative of phi, you can try to do the computation that we did in the morning or in the first session. And you get this. You get a derivative that looks like, let me go there. You get a derivative that looks like t minus 1/4. Really, whatever you're assuming is going to show up. Okay. Plus, this is the derivative. If this goes to 0, then the derivative is constant, is equal to this thing. Now, phi of 1, that will imply that phi of 1, so RS implies phi of 1 is about the same as phi of 0 plus, if you integrate, phi squared over 4 is the plus. This is a minus. Right? Phi of 0 is the decoupled model. Right? When you have the decoupled model, you get exactly this expression. Now, the q squared over 4 that showed up in the RS formula really comes up from here, right? But this doesn't tell you how to prove that this is 0, so you're going to have to work independently to get that to 0. This is just another way of doing it. But you're going to have to prove this. Okay, let me perhaps stop talking about the cavity and then do AMP. So AMP is an iteration, and it is derived from belief propagation or message passing on a sparse graph. So this is the dense version of that. And these iterations are typically designed to compute means. They're really for doing inference, computing marginals of variables. If you have a complicated system of random variables like the one we're seeing here, and I ask you to compute the mean of those variables, the marginals, then you can use AMP to do that. And the iteration looks like this. So if you have an input matrix, it doesn't have to be a matrix, it could be a tensor, but let me just talk about matrices. It's n times n. The iteration will look like u, l plus 1, l is my iterate count. It will be a times m, l, minus a constant to be l, ml minus 1. And what is m? M is a function of ul. And you can start the iteration, for instance, taking u or m minus 1 to be 0 and m0 to be whatever you would like, fixed. And you get to choose the function f at every iteration. You can get to choose them however you want. So this is the one version of AMP. There are many versions of AMP. There are more general things that you can do. So what is B? BL is determined. It's something that the theory tells you. If L prime, few IL. So this is the iteration. So why is this interesting? So it's interesting in many ways. If this matrix is Gaussian, And it's normalized by square root n, so that's the operating, it's order 1. The matrix is order 1. Then the iterates, because of this guy, because of this term, this is called the memory term, the iterates are Gaussian. They're not only Gaussian, but you can exactly compute their marginal, their covariance. You can track at every iteration, you can track the covariance of this Gaussian process, right? And that's very useful. And I'll show you how, perhaps if we have time. So you can do many things with this. One of them, as I said, is to compute marginals. You can use this for many other things. Okay. So in my particular case for the Spikes-Victor model, we're gonna let A to be the matrix Y that we had, but Y, I have to normalize it correctly. I'm gonna have to divide it by square root n. So that the operating norm of this thing is just order 1. So in more particular, this is what it is. The matrix A is that plus this. And you can do the iteration over this matrix, whatever functions you're trying, whatever you like here. And then you can ask whether you can estimate the spike using this iteration. Right? F of L is a sequence of functions that you get to choose. The theory doesn't tell you what they should be. Okay. So let me show you a theorem that characterizes the behavior of this iteration. So this is called state evolution. This is the main theorem that shows up in AMP. Whenever you're using AMP, this is very useful to know. As I said, so this theorem characterizes the exact distribution of these iterates, U and L, and any function of those U's and L's. So let me write it. So for any, perhaps I should write assumptions. Okay, let me just write the theorem without assumptions. Any pseudo-Lipschitz functions, just a version of the theorem, Psi that it goes from R2 to R. And I'm going to explain what this means. We have, if you look at the empirical distribution of the entries, the phi evaluated at UIL and X0I. So this is the spike that doesn't depend on anything, right? So this is just the, but why UIL is generated from this iteration, right? Then this thing will converge as n goes to infinity to an expectation of the function. And then instead of having a U here, we have the following. We have a mu L times X0 plus sigma L times Z. And here we have an X0. Okay, let me tell you what these things are. X0 is drawn now, it's univariate. It's drawn from the prior. Z is univariate. It's drawn from a Gaussian. And I have to tell you what these numbers are. This is a sequence of numbers. So what is that sequence of numbers? It's determined by the following iteration. UL plus 1 equals square root lambda, expectation X0 times FL of this. Sigma L Z. And now what is sigma? Sigma L plus 1 squared is expectation of FL of the same thing. UL X0 plus sigma L Z squared. Okay, so this is my iteration. You're going to have to start it somewhere, this iteration, and that will depend on where you start your algorithm, what this M0 is, or what's the U0 is. So for instance, if you have an initialization that has the following properties, if M0 x0 over n converges if converges to a parameter tau, and the norm squared of this 10 over n converges to a parameter rho, then this iteration will start from mu0 equals tau and sigma 0 squared equals rho. Okay, so it will depend. So the initial conditions of this dynamical system will depend on how you initialize your algorithm. So what does this tell you in perhaps in just morally, let's say? It tells you that the coordinates, forget about this. It tells you that the coordinates of this iteration, the coordinates of your algorithm when you iterate over the algorithm, the coordinates have the same law as this. When you draw the histogram of your vector, this is a vector of n dimensions, right? It's an iteration of n dimensions. Draw the histogram of that at iteration L. Right? The histogram will look exactly like this law, right? Look like an x0 multiplied by a constant plus a Gaussian multiplied by a constant. That's the histogram. Now you do another iteration, L plus 1. The same thing is true with an L plus 1 here and an L plus 1 here. So it's an exact characterization of the behavior of the algorithm at every possible step, right? This is like a very strong thing. Like if you do gradient descent, you have no idea what the intermediate iterates of gradient descent do. You just know that it converges if the function is convex or whatever, right? So this is an exact characterization, which is very useful. Are there any questions?
Do you need any conditions on how you choose FL?
FL have to be, so I didn't talk about the assumptions. Assumptions. FL have to be Lipschitz differentiable. And what is pseudo-Lipschitz? Pseudo-Lipschitz mean, I think this just also needs to be pseudo-Lipschitz. I'm not exactly sure. I think you can make the theory work. Pseudo-Lipschitz. What is that? That's just almost Lipschitz, but I allow you more slack. Okay, so Lipschitz is this, right, with an L, and I allow you a linear growth in the Lipschitz constant, right? So this is, for instance, satisfied by the square, x squared. X squared is not Lipschitz, but it is pseudo-Lipschitz. So I can put an x squared here and everything works, right? And that's useful. You don't just want Lipschitz functions, you want more general class of functions. Yeah.
And I guess here you can use this characterization to design how you choose FL. So
exactly. So that's what I want to talk about now.
Why is it called approximate message passing?
Because message passing is, well, this is just because of historical reasons. The thing that was known is message passing, belief propagation. You know, you have a graphical model, and then you just pass messages, right? So you have, right, this guy will send a message. So the neighbors of a particular vertex I will send a message to a vertex of that vertex I, and then something happens here. You have a local computational rule that combines these messages, and that's sent to this one, right? Now, if you look at a dense graph, you can still do the same thing, but then you have an n squared number of iterates that you have to track. But it turns out, since the graph is dense, the message that I is going to send to J is the same, almost the same as the message that I is going to send to another neighbor of it. So you can just remove the dependence on the receiving end of the message. Okay. Now, if you want to make this work, actually in the iteration, I didn't do this because I don't have time. If you want to make this work in the iteration, you're going to have to subtract this term. This term has an effect. When I say that you can ignore the receiving end, you can ignore it by making this correction. Once you make this correction, then everything's fine. And that's why it's called approximate, is because you're just sending the same message to everybody. I'm not personalizing my email to you particularly. I'm just going to send a mass email to everybody by using this correction, and it will work. It's the same. So now the behavior of the two iterations is the same. That's why it's called approximate.
UL is like ML is the
yeah. So UL, yeah. So there are these two. So it depends on the particular application of this. So here, UL is some kind of observation. So when you look at UL from the characterization here, UL almost looks like this. So it's some kind of observation that you get, an effective observation of the signal x0, and ML is a denoise version of it. So ML will be the thing that you're going to estimate with. So in our language from the previous lecture, UL, you can think of it as Y, and M, you can think of it as the posterior mean. So this brings me really to the choice of these functions. So how do you choose these functions? Suppose you want to estimate optimally. How do you choose the functions to estimate optimally? Right. Now, suppose you're in the middle of the iteration. Suppose that you've picked, so this is a recursive argument. Suppose that you've picked FLs up to iteration 10 or something. Now I want to care about iteration L+1, and I want to know how to pick FL at iteration L+1. Now I know that state evolution is correct, right? And at iteration 10 or L, whatever, the histogram of the U's looks like this, right? So you get to observe U, this new U that you computed, and you know that it looks somewhat like this. It has a histogram that looks like this, right? So it's as if you've received a linear, observation from a linear Gaussian linear model about the true signal that you're trying to estimate with these parameters, right? With this, this combination. Now, if you do that, and I ask you, if I give you a linear model and I ask you how to compute x0, how to estimate x0, we did this. This is exactly what we did in the first lecture, right? So if you receive YL, excuse me, that looks like that. Sigma LZ, observe this, and estimate x0. So what is the best thing you can do? You can do the posterior mean. What is this? So, okay, so you do the computation. Whatever it is, I have it here. Posterior mean is this. Mu t over sigma t squared. YL x minus blah, blah, blah. Zero dp0 of x over the same thing, right? Now I'm going to pick my functions to be just that. Say, take f of u L to be that. So I reduce the choice of trying to optimally choose these functions into an estimation problem. At every iteration, I have an estimation problem. I have a denoising problem to solve, and it's a one-dimensional denoising problem, right? So if I try to just solve the one-dimensional denoising problem in an optimal way, in an optimally Bayesian way, it's obvious what this choice should be, right? And that's my choice. Okay. Now, if you do this, it turns out now you can prove, and it's very easy. Now, one can show that mu L equals square root lambda times sigma L squared. So this bivariate iteration just collapses to one iteration under this choice of FL. So you only have one iteration to care about because you have that relation. Okay. Now, based on this, let me define a reduced parameter, and I'm going to call it QL. And I'm calling it QL for a reason, because it's going to relate to the Qs that I was writing for the RS formula. QL will be 1 over lambda okay. Now, if I look at this iteration and then I try to convert it to give me an iteration over QL, I find the following. QL plus 1 equals 2 phi prime of square root lambda QL, where phi prime is the same function that showed up. Let me write it again. Exponential square root r y x minus r over 2x0 dp0. So this is the function that showed up in the RS formula. Okay. So you have a one parameter to track the behavior of your algorithm. Okay. Now, what do I care about? You may care about many things. One thing that I particularly care about for this iteration is the overlap between my estimate and the spike. Okay. So that's one thing I can care about. You can show that that converges to QL as n goes to infinity for all L, right? Because of state evolution. So this left-hand side looks like the left-hand side here for a specific choice of the function psi, right? If you take psi, if u x0 to be u times x0, right? This is that, right? And now if you compute the right-hand side will be indeed QL. And these are simple computations that you can do. Another thing that you can care about, for instance, is the norm of this. Okay, to norm of this, that's the same thing, Q. Okay. Now I have this convergence. Now, when you take many iterates, you want to know where this converges. I mean, when L goes to infinity, right? It suffices to study where this sequence converges. This is a univariate sequence. You can try to study it. So it's a fixed point equation, right? So just that, just a fixed point equation. So how does this fixed point equation behave? Perhaps I'll go over by 1 minute or something. Thank you. So this is Q. This is the 45-degree line. And I'm going to plot 2 times psi prime. So the function I'm going to plot is 2 times psi prime of square root lambda Q. Right? So when I choose the prior to be mean 0, turns out that this function starts here. Now, what matters here is the derivative of the function at 0. If you compute the derivative of that function at 0, so let me call this phi of q, maybe. Turns out that, as I said, this is 0 if the prior is centered. Derivative happens to be lambda. Lambda times the variance of the prior. If the variance of the prior is 1, this is just lambda. So depending on whether lambda is greater than 1 or smaller than 1, the thing will go either up from the 45-degree line or below it, right? So if lambda is smaller than 1, the thing will do something like this. If lambda is larger than 1, the thing will do something like this. Okay, lambda smaller than 1, lambda larger than 1. So here you see that the only fixed point is 0, in which case you're going to converge to 0. This iteration will converge to 0, and you're completely orthogonal to the signal. Now, if lambda is larger than 1, there are 2 fixed points. There is this one and this one. It so happens that this is the optimal thing that you can do. This is the Bayesian, if you do posterior mean, you're going to get this value of overlap. Now, if you do AMP, so you're going to have to track this fixed point iteration. Start anywhere you'd like. Let's start here. You can even start here if you're more careful. Okay, let's start here. This is where I go, right? So we converge to that point. It's just a fixed point iteration. Okay, that's nice. So for functions, if I didn't lie to you and the shape of the function is exactly this, then this is what happens. And you see that the behavior of the algorithm is more or less the same as the behavior of the spectral method, as far as these critical threshold is concerned, it's always 1. So, but there are situations where the critical threshold is below 1, in which case my function will look like this. So it'll still start from 0. And it will, instead of being concave like this, it'll do this. Okay. This is for a low lambda. Now, if we start increasing lambda, increase lambda a bit more, you have 2 intersections. I don't want this. Oh. The point is lambda is strictly smaller than 1 here. Right? Lambda is still strictly smaller than 1 because this is what the curve looks like. The derivative here is lambda. And if the derivative of the curve is below, that means that lambda is strictly smaller than 1, right? Still, you still have 2 intersections. Turns out that this one is unstable, this one is stable. This is Q star. This is what the optimal Bayesian method will give you. If you were able to compute the posterior mean of the measure, of that Boltzmann measure, we would get an overlap that is here. This is the overlap. This is the optimal thing, right? But now try to apply AMP to this. So forget about these 2 curves. Let me remove them for clarity. Okay, I don't know how clear that is, but okay, let's see. So if I start here, let me start here. So I go here, but I'm gonna have to go left. This is the stable fixed point. I go to 0. I don't go here, I go here, right? So your algorithm is still drawn to the non-informative fixed points. This is why I call non-informative, because its ortho gives you a state that is orthogonal to the true signal, right? Even though the optimal thing tells you that you have to be here, right? So this is a computational phase transition. It always happens at lambda equals 1, regardless of what the optimal, the Bayesian information theoretically optimal thing is to do. So for this type of problems, the problem seems to be hard algorithmically. I don't know how to solve it. It's information theoretically possible. I have no algorithm to solve it. AMP doesn't solve it. And yeah, we don't know of any algorithm that can solve it. An example of such a problem, okay, I have to wrap up. An example of such a problem is Sparse Pca, where the prior is a 3 delta prior. So when you have mass rho over 2 over minus 1, let's say minus 1 over square root rho, plus some mass over 0, plus mass over plus 1 over square root rho. I'm dividing here by square root rho so that the prior is still unit variance. It is mean 0, but for a rho small enough, which means that you're putting enough mass on 0, then the curves will indeed look like this, right? So this is a discontinuous phase transition. Phase transition. Why is it discontinuous? Phase transition. As you're changing lambda. So recall that movie that I showed you, the few frames of a movie that I showed you about increasing lambda and how the curve looks like. It starts like this, and it starts increasing, but it has a bump here. So at some point, the bump is going to touch this line, and you're going to have a critical point that's going to show up. That critical point showed out of nowhere, right? Because before that, the only critical point was 0, and you suddenly jumped from 0 to something that is strictly positive. So if you draw Q star, if you draw Q star as a function of lambda, this is Q star of lambda is 0, 0, 0 up to this value that is critical, and then you go here, and it starts increasing, right? This phase transition is continuous because if you try to do the same movie again, this picture will look like this, up to lambda c, which happens to be 1 in this case, and it'll do this. So we see that the order parameter, this is called the order parameter, it has a kink, but it's continuous across that transition. Here, it is discontinuous, it has a discontinuous jump. Okay. So this is a marker of computational hardness. Okay? Discontinuous phase transitions are bad as far as algorithms are concerned. Because now if you do AMP, I told you it only works up to when lambda is greater than 1, so you're going to have to wait up to lambda 1. So AMP will be like this. And once you get to lambda equals 1, then you jump and you follow the optimal curve. Here. Okay? In this problem, AMP will just follow this curve always. Okay? So there is no computational hardness here. There's a computational hardness here. Okay. Figuring out whether phase transitions are continuous or discontinuous is an old problem. And okay, so the Fields Medal was awarded because of figuring out that certain phase transitions are continuous and certain others are discontinuous, but not for this type of models, for the Ising model in finite dimension. So let me stop there, and then I'll see you tomorrow.
I guess we can.
So before we break, so the next thing will be at 1:30 panel. And we have a website, or if you want to, where if you have some questions that you'd like to ask or vote on questions that other people have, but it's fine. Slido.com. The code is 1.